All right, let's dive into a crazy, high-stakes story that's unfolding right at the heart of the AI revolution. And it turns out the biggest challenge isn't about making chips faster, it's just trying to stop them from literally melting.
It all kicks off with a huge mystery. You see, we just learned that Nvidia, the company that basically dominates AI, made this sudden, super urgent change to its next generation chips. Now, a change this late in the game? That's almost unheard of. It tells you something big, something they didn't see coming, must have happened.
And to get to the bottom of it, we've got to talk about a few things. We're talking hard physics, a seriously fierce corporate rivalry, and one single little component that's about to change, well, pretty much everything about the data center. Okay, so here's the timeline. This is what the supply chain is telling us. The original plan was for Nvidia's 2027 chip, codenamed Rubin Ultra, to introduce some new cooling tech. But then something changed. All of a sudden, that 2027 technology got yanked forward. They scrambled to get it ready for an earlier chip, the Vera Rubin, which is now launching in late 2026. This is a huge, expensive shift, so what gives? Why the last-minute fire drill? All right, to figure that out, we have to zoom in on the scene of the crime. We're talking about the chip package itself and this fundamental problem of just trying to get the heat out. Okay, so for the longest time, this is how we've cooled these high-performance chips. Think of it like a little stack. You've got the silicon die at the bottom, doing all the work, getting crazy hot. That heat has to travel through a first layer, into a copper lid that spreads it out, then through a second layer before it finally hits a cold plate where liquid can whisk it away. It's a 5-step journey. And for years, this system worked just fine. But as AI chips got more and more powerful, one of those layers, that second thermal material, the TIM2, it basically turned into this epic traffic jam for heat. It's a physical wall that today's AI chips are just smashing right into. And this slide just lays it all out. Look at the numbers. The copper lid is like a superhighway for heat, a thermal conductivity around 390. But that TM2 layer, which is really just a fancy thermal grease, it's a slow, clogged side street with a conductivity of maybe 5 to 10. You can't escape a burning building if the main exit is a tiny little door, right? Well, you can't cool a superchip through this massive thermal bottleneck. So yeah, we've got a physics problem. A big one. But just hitting a thermal wall, that's not what really lit a fire under them. The real reason for this panic: competition. Welcome, my friends, to the TDP arms race. In the world of AI, thermal design power, which is really just a fancy way of saying how many watts a chip can handle, has become the new battlefield. It's not just about who has the smartest chip anymore. It's about who can handle the most raw, brute force power. And this right here, this chart tells you everything you need to know. Nvidia's original plan for their next big chip was a super ambitious 1800 watts. But then they got wind that their main rival, AMD, was gunning for a colossal 2500 watts. All of a sudden, their 1800 watts looks, well, kind of weak. To stay king of the hill, Nvidia had to react, pushing their own chip to a jaw-dropping 2300 watts. And that, right there, was the breaking point. See, at 1800 watts, the old cooling system was already on the brink of failure. At 2300 watts, it becomes physically impossible. It just doesn't work. Game over. As the quote says, that heat traffic jam at the TM2 layer eats up the entire thermal budget. There was no way forward. Nvidia had to find a completely new solution, and they had to find it now. So with their backs against the thermal wall and a competitor breathing down their neck, what they do? Well, they turn to this incredibly elegant piece of engineering that really is the hero of our story. It's called a microchannel lid, or MCL. And check this out. The idea is just brilliant in its simplicity. Instead of putting a cooler on top of the chip's lid, you make the cooler become the lid. They machine these tiny channels, some thinner than a human hair, directly into the copper itself. The liquid coolant flows right through the lid, just microns away from the source of all that heat. I mean, just look at the difference here. It's night and day. The old way was bottlenecked by that TIM2 layer. The MCL, it just gets rid of it completely. And the result? The max power it can handle just skyrockets from around 1800 watts to over 3000. And check out the vendors. This isn't just an upgrade, it's a changing of the guard. Specialized companies like Jentech and AVC are now front and center. So the new path for heat. It's so much shorter, so much more efficient. You go from the silicon through one interface and bam,
directly into the liquid flowing through that microchannel lid. That old 5-step journey just became a 3-step superhighway. But here's the thing. This one tiny change on the chip has this massive, massive ripple effect. We're not just talking about a new component anymore. We're talking about a completely new kind of data center. Get a load of this number. 600 kilowatts. That's the power density of a single Nvidia server rack using this new tech. That's enough electricity to power dozens of homes, all concentrated in one cabinet. At that kind of density, blowing air on it isn't just inefficient, it's totally, completely obsolete. So, the big takeaway here is that this one decision forces an entire infrastructure revolution. Now, data centers are going to need facility-wide plumbing. The demand for specialized high-pressure pumps is going to explode. And the whole value chain shifts away from just stamping out metal boxes to the companies that have mastered precision fluid dynamics. Players like Jentech and AVC are now absolutely mission-critical suppliers in this new AI ecosystem. So this microchannel lid, it solves the 2300-watt problem of today. But we already know there are 5,000-watt chips on the roadmap. This is clearly just a stepping stone. And it leaves us with this one last kind of mind-bending question. If the cooler has already become the lid, is the final frontier to make the chip itself the cooler by building liquid channels directly inside the silicon? The heat war, it is far from over.